record on this computer. хорошо. Let me share the screen.
Maybe it would be good, for example, to send for us, for example, from Sorbonne University, how they like provide such things, or
Okay,
like
gotcha.
example of such a Google Note, for example.
Yes.
That's to see.
Yes, that's a good question. Let me check it. I think it's this one. So it's in French, so I don't think you guys would understand many, but you'll just understand the structure easily. So can you guys see my screen?
Yes.
Yes, we can.
So basically, we start by creating just a small Google Docs shared, and we put the structure, the program, some questions and stuff like that, and then basically we just put this. So the teacher will just put for example, the title of the sections, and the students will be the ones who will create the rest of the lecture. So basically, you guys will just be writing the questions that you find interesting and answering them in here. So basically writing your own lecture notes inside the Google Docs. We will try this one a bit later. So for now, let's just go back to the, okay. So I'm not really sure how many of you guys already have done this and haven't. So we will go through it, and if there's something that you guys are already familiar with too much, then you can just tell me in the chat to just go through it even faster. So for those who already have taken the course of advanced machine learning, I am sure you have already done this because you've done this with me. But for those who haven't, so for the first years and maybe for the second years of robotics, if you guys haven't done this, just tell me where to focus on and what to skip quickly, okay?
Okay. Yes.
Okay.
So basically, before we start, this lab is going to be a very simple lab. So basically, this is just the introduction of the first week's material. So it's going to be about image classification, transfer learning, how to freeze the weights, when to freeze the weights of the encoder, what's an encoder, what's a classifier, what is latent space, what are embeddings, stuff like this. And then we will just see how to do this with a PyTorch example. And then for the sake of this course, since we will be since you guys will go to different branches, some of you will go to research, some will go to industry, it's very important to be able to just switch between PyTorch and TensorFlow whenever needed. So just this is like a complementary part where we will just see how TensorFlow code would look like for a small MNIST classifier, okay? But the main part will be on PyTorch since it's the easiest one to use. TensorFlow will also describe it a little bit, but it's I recommend if you can just avoid it, then just go directly for PyTorch, right? The ImageNet competition. So this was the kind of the boom that happened for computer vision. I think it was around like 2014 or something like that. So basically, they created a very large data set with lots of images and lots of classes, and that allowed researchers to advance and create new, well, let's say, create new architectures for computer vision, for image classification. And that gave us a certain benchmark to compare different image classifiers against. Some of the classes that you can find here are definitely, for example, a husky, dog, working dog. So there's like a simple, what do you call? So there are lots of hierarchies inside this data set. And I think the hierarchy is found on another data set called, I forgot the name, but it's some sort of a hierarchy for like nouns and verbs and how they connect, and they chose only the nouns from this hierarchy. As you can see, the images are actually very clear and very easy to see. Let me admit the students. 1 second. Nice. If somebody has not been admitted, just send a message on Telegram. But you can't hear this because you're not admitted, right? So the winners of this, well, let's say challenge, I think the challenge is no longer operational because right now they have largely finished this challenge. So here we can see the shallow models. Shallow models are like any model which does not use really like deep neural networks. The first one was AlexNet with 8 layers, and this is their error rate. So 16%, so let's say 16 images out of 100 were misclassified. And right after that, neural networks have continued getting bigger and adding some special components, different types of layers, and reducing this error of the model to a level even better than a human being. I think right now, the only reason why we still have error inside this data set or inside this challenge, it's mainly because we don't have, what is it called? It's mainly because the labels in this data set kind of are not fully correct. So for example, in the same image, you can find a dog and a cat. So these kinds of problems in the data set itself make it difficult to get like 100%. But other than that, I think it's with what we have, I think we can easily get to a very good level for image classification, especially if we have a big data set such as ImageNet or something even bigger. Using pre-trained models. So if you guys would like to build any image classifier or later on when we'll be building, 1 second. Okay, nice, accepted. Nice. So if you guys will be building stuff such as image classifiers or object detectors, you're definitely going to be starting from a pre-trained model. So pre-trained models are just a big model that was trained by a big company such as Google or Facebook. So usually the features or the layers and the weights of such models are very generalizable or very generic and can be used in different scenarios or different tasks, right? Here are just a simple list of what can be found inside PyTorch models list. So here we can find stuff like ResNet, AlexNet, BGG, DenseNet, Inceptions, Google Nets, mobile nets are very useful. So basically you can find all of these and they're already trained. You can choose whether to keep some of its parts, whether to remove some of their parts, and this will be your choice based on how much data you have. So I'm sure some of you guys are already familiar with this. So can you guys tell me when should we keep or when should we, for example, freeze the weights of the encoder and when should we keep them trainable?
For example, if you want to stay trainable, in this case, if you have your own data set, for example, but it's much like less than ImageNet, for example, in images, and you want your model to be trained on this model set. And in the case of like avoiding the overfitting or maybe early overfitting, you need to like to allow the weights to be trainable, but use your own data set in this case, but not freeze weights. And second scenario is about when you want to use your model, not like a model itself, but like a part of like pipeline, maybe like a feature extraction. In this case, you don't want these weights to be trained because it's non-unique in this, and you freeze the weights. And maybe like change the last fully connected layers for your own purpose.
Got you. So can somebody give me a Can somebody give me
It was scared.
Yeah, that scared me. Can somebody give me a another explanation? So basically, or another point of view.
So if you wanted to change the shape of the input and the shape of the output, you change the like you train the first layer and the last layer, but you keep the weight same.
Somebody give me another point of view. So this point of view, I'm speaking about how many samples do you have inside your data set, your new data set, okay? Well, 1 second, yeah, go ahead.
So,
Mohammed, yeah, go ahead.
My name is Awais. There is a problem with my microphone. Can you hear me well?
Yeah, we can hear you pretty well right now, yes.
So I asked 2 questions in the chat. My first question was regarding ImageNet, and then the answer to your question is that this is my point of view. When we want to use structure of model, we just use trainable model, and when we just want to use the weights of previous model, like somebody already mentioned that we just use fully connected layers.
I didn't understand correctly the second point. Can you repeat it?
The second point is we just keep the layers freezed or model freeze when we want to use the weights of previous model and just change the shape of output.
Okay, got you. So the point of view that I was looking for is, so of course, all what you guys have said is of course logical and correct, but what I wanted to see is when, for example, you have a very large data set, you can't afford to start at the ImageNet weights and then just fine tune them further on. So basically, even the encoder will not be frozen, okay?
Well, definitely we need like freeze layers to keep the speed of training.
Yes, but
high speed.
Of course. So if you'd like to increase the speed of the learning, or for example, you don't have enough data to actually learn good features, then you should freeze as many layers as possible and use them in your model as they are, and just, for example, train from scratch only the final layer of your model, right? But if you have enough data, for example, I don't know, you have 100,000 images, in this case, you can keep the encoder part training. So you start from the pre-trained model of, for example, ResNet, and you don't freeze it. You continue training on it, okay? Why is that? So mainly because the ResNet model is very useful for feature extraction. So it has learned many discriminative filters. But if your model, for example, or if your images come from a different distribution, let's say. So for example, you're working on medical images, you're working on paintings, you're working on sculptures and stuff which are not really found inside the ImageNet dataset. In this case, you might want to retrain even the first layers of the CNN. So do not start from scratch, of course, but allow your feature extractors to kind of get an idea on what are the different styles and shapes inside your data. This will help you improve your results even further. I see that Mohammed Awais wants to, yes, go ahead.
Isn't all data going to be destroyed by catastrophic forgetting?
Can you repeat this?
I mean, because of catastrophic forgetting, all data going to be useless if we not fix it, right?
So basically, you mean that the things that you learned from ImageNet will be forgotten after you train on?
Yes.
Yes and no. So basically, you started at a good point for your own data set, and then you are trying to improve for your data set. It's true that if you use the new weights on images from ImageNet, it's not going to work. It's going to be very bad on it. But if you have enough data in your own data set, this method would give you better result on your own data set.
If we have small data set, we are fixing as much as possible. If a bigger one, we can flex a bit.
Exactly. So if you have a small data set, then try to freeze as many layers. So of course, all the CNN layers, all the convolutional layers, and even if you can, go ahead and just freeze some of the fully connected layers. Go ahead, Ali.
I want to like introduce my point of view for this
Yes.
problem. Actually,
Uh-huh.
and from my experience, actually, I may say what pre-training is good not only for like big data sets, because you want like to shift the ImageNet from one distribution to another distribution, but also for small data sets, because there is like plenty of scenarios when you have like images from your own sphere, but amount of these images are not enough to saturate the deep models. For example, ResNet is especially very difficult. In this case, you pre-train your like model on ImageNet, and then like take some dozens of epochs on your data set with pre-training, with like keeping weights training, and it will work also. And second one, I think. But I think it's good. But this was my point about this.
Got you. So definitely, yeah, definitely. If you have a small data set, then you should not try risking retraining. You should kind of start by just keeping as many frozen layers as possible. Yeah, because your model is never going to be trained from scratch. It's never going to be enough. I think Mohammed Awais also wanted to say something.
Yes, my question was like, I want to use 10 samples from each class of ImageNet. Can I use like subsets of ImageNet dataset?
Yes. So just one thing maybe you should focus on is make the subsetting operation not very random, not randomized. So try to make it as regenerable as possible, just so that your results are what they call it, consistent.
The question here is like the selection is not a problem. Like I don't want to download 156 GB of ImageNet dataset.
Haha, got you.
Yeah.
That makes sense. That really does make sense. I'm not sure if that's possible. I'm not sure if that's possible. I think the best way would be just to get it done over Colab. I'm not sure if Colab allows you for 100 and
Colab is 70 or 100 GB, like less than.
Yeah, I think maybe try to find a smaller version of ImageNet somewhere.
Yeah, I will find it. Thank you.
Yeah, or locally. Locally it's doable, but yeah, it will consume a lot of your space. Yeah, true.
Could you please explain sum up again when we need to freeze the weights? Could you please just sum up?
Perfect. Yes. So let's write it here. Fine tuning.
And priority of which weights to freeze.
Yes.
And
so
freeze.
Yeah, fine tuning means no freezing of any layer. So basically, we start from a pre-trained model and then continue training the weights. All the weights are being trained. We do this when we have a lot of data. Freezing and training from scratch. Not from scratch. That's yes. So freezing, pre-trained, and training from scratch, the last layer, right? Not enough data. So saying a lot and not a lot, it depends on how many classes do you have. Technically, you can say if you have more than 10,000 image per class, you're definitely in the a lot area. If you have less than 100 per image, then you're definitely in the not enough area. Yeah, 1 second. Let's just continue the wrap up, and then I will allow for interventions. Yes, the priority for freezing goes for the first layers. Yes, so try to freeze the first layers of the model as much as possible, because the first layers are usually only learning stuff such as what is an edge, or what is a vertical line like this, or what is this shape like that, the shape of the hair. So stuff like this. And then the second layer would be what is a cycle what is a triangle, stuff like this, very easy and basic and generalizable features. Now, if you go to the last layers will be learning some maybe dataset specific information, such as the whole face. So they're trying to connect all the dots to the whole face, the dots to the images, to the eyes of the dog and stuff like that. So does this answer the questions? I think, Anton, you asked for it?
Sure, sure, yes. And the question is, are we gonna try to freeze today, or some weights, or are we gonna?
Exactly.
Yeah. Thank you.
Yes. So basically, we will be doing training from scratch, and then we will be doing just a simple model with freezing. I think Ali, and I think Ali, 1 second. I think Mohammed Awais was before, right?
Yes. So my question is regarding freezing the layers.
Yes.
Like, how do we define we don't have enough data? Let's suppose we have to categorize different dogs, and we don't have a class of dogs in our data, and it is not existing in pre-trained model. So we have like very less data in our right now, and we have a pre-trained model in which there is no class of a specific dog. So what should we do in this case?
In this case, you're not really speaking in the area of transfer learning. I would say you are in the few shot learning area. In this case, usually there are different models. I think there is a good paper on hierarchical novelty detection. This one can be very useful if you don't have any image of the class that you are trying to learn. So yeah.
The question is, like, in pre-trained model, they were not discussing about this breed, but now some scientific changes happened, and now there is a new breed.
And there are images of this breed, or no?
There are images right now, but when the model was trained, there were no images.
That's okay. That's okay. Then you are in the transfer learning stage, and that's very simple. So basically, as we just said, if this new dog breed is like completely different, and instead of looking like a normal dog, it looks like a water bottle like this, then yes, you're gonna need to retrain mostly all of the convolutional neural net layers. But if this new breed of dogs looks like a very similar, looks like your everyday dog, but just has a simple changes. For example, the color of the skin, or maybe the size, or stuff like that. So maybe it looks like a dog. It's still very recognizable as a generic dog, but it has its own specialties. In this case, you should just freeze most of the convolutional layers and then just fine tune the final layers of your model.
Here, why I asked this question, the reason was, won't be it causing the problem of class imbalance, like there will be imbalance of classes.
Yes, and that's okay. If you have the problem of class imbalance, the way to solve this problem is to just Google how to solve class imbalance, and then you will find lots of information on doing that, either sample weights, either changing the, yes, so basically sample weights is a good one, upsampling, downsampling. There are many techniques you can fix the problem of imbalanced data, but this is like a kind of a separate problem.
Thank you.
Yeah, so basically try to fix first the scenario of transfer learning, and then add to it all the tips and maybe tools that you can use for solving imbalanced data issues. Ali, did you want to add something?
Yes, it's actually a little bit about the fine-tuning pre-training. Actually, when we want to do fine-tuning pre-training, we need to take into account what models were trained for standard set and for some reason, like for some task. And actually, if your task is far away from what model was originally trained, and if your data set is changing, like the distribution of your data sets are too far away, the pre-training and fine-tuning may have no sense. It's just like a small remark.
I really like, yes, I really like your description. I think there was a very good table. Yeah, this one. There you go. Right. So if you have a similar data set with a small data set, so this is for the source data or the original data set. If it's very similar, then just try to do transfer learning, highest level features plus the classifier. So for example, you can fine tune only the last layers of your model. If you have a small data set with a similar data set, if you have a small data set, again, you don't really have a lot of, what is it called? A lot of, what are they called? Help me out. You don't have a lot of freedom. Yes.
Okay.
You don't have a lot of freedom to keep the retraining done from all the layers. So in this case, you will still need to keep the first layers frozen and only retrain, for example, the last 3 convolutional layers with the fully connected. Okay. So this is the case when you have a small data set with different pre-trained data sets, right, from different distribution. A very good example is using an ImageNet model on medical images or MRI scans. This is a very different type of images. You're not working with the same higher level features at all. If you have a large data set, now whether it is a similar data set or a different data set, you can afford to do the fine tuning. So you don't need to freeze any of the layers, fine tune them directly. So start from a pre-trained model and then fix all of the weights according to your data. This way, you will be learning even better low-level features, which will be tailored to the shapes and styles of your images. And of course, the high-level features, which are completely different and are very dependent on the objects inside your data, they will also be very fine-tuned and they will work very well for your data set. So again, the concept of whether the data source data is similar or not only occurs if your target data set is small. So this problem of whether I should freeze or not is only something you should worry about when your data set is small. If you have a large data set, don't freeze anything and fine-tune all the layers. If you have a small data set with a similar data set, then freeze as many as you can and just retrain the last layers. If the 2 data sets are similar, then try to only freeze the first 3 layers of the convolution, and the rest should all be fine-tuned. Let's take this image. Yes, Jan?
Okay. Question. If
Yes.
we have our starting data set, for example, dogs, and it was used for classification of dogs, but we are training, our task is to classify some diseases across dogs. So our images can be, I mean, our images close enough, but objective of classification was completely different.
In this case, yeah.
Yeah, so we still considering these data sets close or it's not?
Yeah, this depends highly on your eyesight. So basically look at the original data set. If, for example, the original data set shows you the whole dog, and here is the dog in front of you completely. But the second data set, which working on the diseases of the dogs, only, for example, shows you this small rectangle inside the dog or the dog's hand. In this case, you're seeing that there is some sort of, okay, let's say it's the students. Yeah, you're seeing that there are some differences in them, right? And mostly the lower level features, which are useful, for example, for detecting the eyes and stuff like this, might not be very useful for you in this case. I'm thinking maybe the diseases that you're looking for are something that is on the skin, very visual. So mainly you are trying to look for stuff such as the color of, for example, a pimple, or the color of the skin, maybe the shape of something that's out of the ordinary on the skin, something like that.
Well, yes.
Yeah, exactly. So in these cases, your source data set is not going to help you a lot with lower level features. If you have enough data set, try to retrain. Yeah, try to retrain even the lower level layers. Yeah.
But if I mean, it's not about diseases, but they are using same pictures. I mean, like for example, entire doc for every situation. But our starting data set doesn't have examples of sick docs. It's gonna help us, or it's maybe
it's definitely gonna help you. Yeah, in this case, it's definitely gonna help you. They're very similar, as you are saying. They're very the same, so it's definitely going to help you perform better. 1 second, there's somebody who's trying to join. Nice. I think yes, good. So yeah, as we said, it's definitely going to help you to retrain from scratch. Not from scratch, but I mean from the pre-trained. So don't use freezing of the layers.
Thank you.
Thank you. Nice. So let's continue, guys. Just wanted to show you a small example of what are the layers inside the ResNet. You guys can see my screen, right? Or let me share it again just to make sure.
Still can.
Хорошо. Can you guys see it?
Yes.
Yes.
Nice. So basically, here's the ResNet. So we have convolutions, which is conv2d. Can somebody tell me what is batch norm 2D or batch normalization? Why is it useful? Does it help? Of course it helps. Does it give you better results? And what is the thing that happens here?
It increases the speed of calculations.
Give me more.
Batch normalization, it if I remember correctly,
Nice.
I think it blocks some of your perceptrons or neurons.
You're speaking about something else. It's very similar, but you're speaking about something else.
Sorry.
Yes, but that's a good one. Please keep it as a note. We will speak about it just right now. Can somebody tell me what batch norm is?
I think first it normalizes some weights
right?
for the data, and it helps in covariance shift.
Exactly. So basically, it's inside the name. So we are normalizing the batch, right? And it comes out comes before, after the layer. So what does it mean? It's definitely going to normalize the output of each layer to make sure that there's not really big differences between the layers. There's going to be more smoother training, more smoother gradients going all the way back.
From the words of NDNG, actually, yes, it's like it's depending your words, like the layers like between each other want to be ensured what data is like some kind of centered or like some examples, some stock standards, and this like will help to model to train in smoothly and much better in this case.
Exactly.
And actually, like there is like a very big difference between where you put the batch normalization in the end or with start maybe, and how many and how and what is like how hyperparameters with batch normalization. Actually, is maybe the most efficient tool for like personalization.
Yeah, got you. So I think from the name in here, you can just guess what are the two best features. So accelerating and reducing internal covariance shift. So this is what Yusuf Misbah just described in his intervention. The next one is ReLU. So I'm sure everybody knows what ReLU is. So it's an activation function, right? MaxPull2D.
As we conclude yesterday, is this filter, but with function instead of
weights.
Yeah.
Nice, amazing. Let's see, any different?
Basic block is just collection of layers, right?
Yes, exactly. So basically it's sorry. Yeah. So basically, as you might have known already, ResNet is based on residual blocks, right? And can somebody tell me what are residual blocks?
It's special
Basically,
kind of.
it takes.
Okay, well, take your word.
Yeah, go ahead. Yeah.
Basically, like the image you just showed, it takes like the input and feed it to a further layer, after
Yes,
you.
exactly. Why is this useful though?
It is useful because it can help to remove the problem of small gradient descent when you've got a lot of layers. The error propagation became small and
Smaller, yes.
So when we use residual blocks, we can solve this problem.
Exactly, that's perfect response. And it also, when you have when you have like lots of layers, some of these, what it does is, if this layer is going to be completely useless, at least it's going to be working as good as the identity matrix, as the identity function, right? So at least it's going to be, it's not going to reduce the performance of the model. Adding this layer is not going to hurt the model. It's only going to make it better, right?
I'm not understanding why it's not.
So for example, if the weights of these layers are completely useless. So maybe you have trained a lot, Ali, 1 second. Maybe you have like trained too much. You have lots of layers. So you have a model with 200 layers. Some of these layers might not be very useful and might be just learning stuff which are, or you don't have enough data to learn them very well. So the easiest thing that they can do is to learn the identity matrix. And instead of doing something very bad, they're going to be doing something similar to the identity matrix and not going to harm the model that much.
But in some situation, I mean, layers can be good, but in some way they can work bad. I mean,
yeah, of course, having too many layers is not always a good thing. As we've said, having too many layers will drop the performances of your model.
I mean, how we measure efficiency of our layer if we have, I mean, for some image, this layer gonna move towards right result, but for other image, this same layer gonna move in direction of bad result.
I really, yes, vanishing gradients is also a good one. I really love your question, Jan. I will not answer it. I would like you to answer this question right after we finish the lecture of model interpretation, okay? So just the second you said this question, it just reminded me of something that we will see in there, and it can be easily said to the same question. So please keep it in mind. So Jan's question. If I forget, please remember it. Just the second that we finish the second lecture, go ahead and give us this question again, and please you answer it yourself, okay? хорошо. So now let's get down to business, right? So we spoke about the transfer learning. If the final layer, for example, has 10,000 classes, whereas your data set has only, for example, 10 classes, then the final layer is completely useless for you. You will have to retrain it from scratch. If the input is in a different size, so for example, this model takes input of size 200 by 200, your images are mainly 3000 by 3000. The simpler thing you can do is just downsampling them or resizing the input image to fit into the dimensions that the model expect, right? Yes, in this example, I will not be showing you how to create data loaders and data sets. So basically we'll be using predefined data, but in the example of the homework that you will be given, you will need to create your own data readers, right? So in PyTorch. It's a very simple task. I'm sure that the people of the masters have already done this. You've done this with me already. For those who haven't, it's very useful to be able to have total control. Okay, let's accept people. Nice. To have this total control over over the data reading process, right? Nice. In here, usually you should split your work into transforms, data sets, and data loaders. So the transforms that you can get in here, so basically we transform them into tensors. So if they come, for example, as NumPy arrays, we convert them into PyTorch tensors, just for speeding up the calculations and taking them to the GPU.
What is transform? I'm not remembering.
Nice. Transforms is just augmentations. Remember augmentations?
Yes, yes.
Nice. So let's go here. Let's say PyTorch transforms, right? Here you will see a list of all the possible augmentations that can be done here. We will not go through them in what is it called, in detail. I like to use another what is it called, another library for these things. It's called Albumontations. So basically here you can find stuff such as let's see, centering, center crop, normalizations. Compose is just to bring different transforms together. So basically make a list of transforms which will be applied after each other. Center crop, color jitter, this is just to play with the brightness, the contrast, saturation of the hue of the images. You have stuff such as 5 crops. This I don't really recommend using it. It's just too difficult to use anything after it. It's horrible. A grayscale, for example, it's very useful. Let's admit this. Yeah, a grayscale is a good option for what is it called? For learning better lower level features. Padding, useless. Randomifying. I've never really found a good scenario where this helped me, but it's very useful. So basically this will just rotate, for example, not rotate, but like if do this to your images. I've never really found it to be very useful, but it could be useful.
I think it could be useful for like paper, for like book scans and something like this.
Maybe, yeah. For example, text character.
Yes,
right.
exactly.
Yeah, that could be very useful. Yes. So, for example, to change from normal to italic, that's a good case. Thank you. Random grayscale, random horizontal flip. So horizontal flip's kind of useful. Just make sure that they don't mess around with your classes. So, for example, flipping a 6 would give you a 9, and that would be very bad. So try to just make sure that your augmentations will not change the class of the model, right? Random rotations are also useful. So these are just different augmentations. So transform are just different augmentations. Yeah, that's direct. So
it's called in TensorFlow with Sunway.
Yeah. Can you say it again?
I mean, it's specifically for PyTorch, or it's also used in TensorFlow. I mean, it has same name.
The transforms for PyTorch. Okay, let's check them. I think PyTorch has its own transforms, but usually you should do them your own by your head, right? Okay, let me check here. I would check, but I usually never really work with the TensorFlow that much. But as I remember, you're gonna have to do them kind of manually. This is what I would recommend you to be using. So if you're going to have something for, I don't know, where a new data set and you're trying to work on either image classification or object detection, this data set really helped me a lot, especially for some of our industrial products. We had some issues with the client saying that the model doesn't work well in this scenario, this model doesn't work well in this scenario. So after just adding a lot of the augmentations in this data set, the model did improve on these results. So I really recommend using this, this library. It's very simple. I think we can just check a small demo. There you go. I want this super pixel thingy just so we can see it. Can somebody see the word super pixel? Super pixels.
Control F?
They don't have it here. I don't know why. Yeah, okay. So
maybe
basically,
it's blue.
Yeah, this is blurring. There you go. Downscaling, right? Flipping. Adding Gaussian noise is very useful to add Gaussian noise. Sorry. Image compression. Nice. Playing around with the channels.
here's anything that's helping with 1 pixel problem.
Yes. So this one again, this rain thingy, it's very useful. Have you guys checked it?
Never
Exactly. Yeah, that's what I said. Yeah, it's amazing for these problems.
And is it implemented in Torch? I mean, Rain.
I'm not sure. I'm not sure how is it implemented. It's very fast. That's what I know. So it's extremely fast. So it's even faster than the implementations of tell me the name of the TensorFlow's library of no, I mean the PyTorch transforms. It's much faster than those. It's very, very, very interesting. And what I really liked was the problems of brightness. So playing with the brightness and playing with the, yes, this rain and stuff, it's much more performant than the TensorFlow, than the PyTorch transforms. So it does give better images and more challenging scenarios. So if your model is suffering from a situation where the brightness is not good or the brightness is too much, definitely using this albumentations thingy is very useful. Another.
The main question of this course is a PyTorch or TensorFlow.
The main question of this course is PyTorch or TensorFlow or Darknet, and these three, you must be able to switch between them without any problem.
But it's like the person can switch, but sometimes there are a lot of dependencies and all the stuff which it's not so easy to switch.
That's what I said. So basically, by default, always use PyTorch, unless there is some constraints that doesn't allow you to use PyTorch. Then you will have to be starting to switch and go to different, for example, to TensorFlow or to Darknet and stuff like that. Okay. So that's why you must be able to switch between these. Some of you guys might be working with future clients, and some client might have an edge device. Others would want you to deploy on the cloud, and these different scenarios would require you to either use, for example, PyTorch, use Darknet directly, or use TensorFlow. And in this case, you must be able to just quickly get your models from one to the other.
What about MXNet?
Nobody would ask.
I just mentioned it.
Yeah, I don't think MXNet is very performant now. I think it's starting to just see the end of the tunnel for that. Yeah, I think you guys should focus definitely Darknet. You must be able to use Darknet's YOLO v4 implementation, train it, change the layers, change the different formats, understand how to tune, how to change the, what are they called, the classes inside the JSONs, and all of these things. You must be able to fix them. Okay. So this Darknet is very important. After Darknet, you can start seeing how to train, for example, object detection models on PyTorch and TensorFlow. But the first thing, you must learn how to do it on Darknet because it's the most compatible with many devices. And it's the easiest to convert to O1NX and TensorRT and stuff like that.
I think every time you're speaking and tell the word Darknet, the government think about, I know.
But yeah, it's in Russia, yeah. So yeah, Darknet is just a simple, handsome repo that we have here, and it gives you YOLO v4 very easily tuned. A very big README in here. I hate it. I would just tell you where to look for the pre-trained models and where to look for how you change the different configs, and that's it. But the rest is really long. It's too long, actually. Yeah, so let's continue. Let's just continue quickly. So here we have the CIFAR 10 dataset. CIFAR 10 dataset, I'm sure most of you are familiar with it already. It's you can consider it as just ImageNet, but with smaller images and less classes, right? There you go. You created the training dataset. You give it the transforms that you would like to apply, and then you send it through the loader. The data loader is the one where you specify, for example, stuff such as the batch size, the number of workers that will be retrieving the images, whether to shuffle the data while getting it or to get it in order. Some data sets, the order of the images is very important, so just keep in mind. And here we have the classes. This is just a small example on how to just visualize some of the classes. So we have the horse class, plane, and the bird. As you can see, this one is pretty difficult to classify, but yeah, let's go for it. This, I suppose that you're already familiar with how to create or how to access the GPU device and send your weights and your data to GPU. So basically, you just create the device, whether it's CUDA. If it's not available, then use the CPU. And here it's telling you that we already have CUDA and we're using the GPU, the first GPU, which is indexed from 0. The second most important part, so we have the first one, which is the data loader part. The second important part in building your PyTorch model is the model or the neural network. In here, you should create a new class that will inherit from your nn.module. This neural network should have two functions at least. The first function is the init. In here, you will define your layers. In our case, we're not going to define, for example, a set of layers or an array of layers. But if you will do that, and probably you will do that, you will need that for your, what's it called, for your homework. You're gonna have to use a specific function call that will kind of read the array of layers that you have, okay? But other than that, so basically you just define your layers and they will be initialized or they will be read by the NN module and initialized later on. The second part, this is the dynamic part of PyTorch. This is the important part. This is what makes PyTorch better than TensorFlow. In here, you are defining the order of the layers. If you would like to make them sequential, there you go. Sorry, 1 second. Huh? So basically, you pass them through the first convolution, ReLU, then pooling, convolution, ReLU, pooling, and then you flatten them. And then ReLU, fully connected neural network, ReLU, fully connected neural network, ReLU, and then last is the classification layer, right? In here, we are completely free to use an if statement. So say if x is binary, x is odd, we go through this layer. If it's not, we go through the other layer. We can do for loop and go through a different array. We are very dynamic in the direction of the data. So the input can flow however we want it, right? It's very Pythonic, very natural. If you have an error inside layer this, your error is going to come here exactly to send you to the exact place and tell you what the error is. I think some of you just raised his hand. Yeah.
No, please continue. I have a question regarding layers. I hope you're going to explain them later.
Okay, got you.
I have a question.
Yes.
How often we visit this part?
How often?
Yes, I mean, for each cycle, we are going to forward or?
Yes, for each batch. So this is the batch. So first, we have the first, this is the batch, what is it called? The batch dimension. The 16 is the number of filters, and the 5 by 5 is the size of the output activation maps, right? So basically, you have dish, right? So X, I think X is like, let's say, batch size, 3 to 150, let's say 150, yeah? So this is the height, width, channel, and the batch size. Okay?
Yes.
We define our neural network and send it to the GPU. This is a must.
Imad, I have a question.
Yes, please, yeah.
Can you please scroll up to the model?
Yes.
So I always have hard time like what to put in parameters of Konokudi and how to link them together. Can you please explain that?
That's a great question. Nobody ever knows how to do this. It's quite a mess. So basically what I usually do, I just simply create first layer, send it here through the data, print the size of the output make the second layer, print the size of the output of that layer, make the third layer, print the size of the output. So usually it's a very iterative process, unless you're some sort of a genius and you can just put the functions and do the mapping in that function that we sent you earlier, get the output and continue ahead, you're gonna suffer through it. So I just recommend you make one layer, put the forward here, and then print x.shape or x.size, right? And then see the output shape, and then make the next layer and make the next layer. So that's it. So try to make the size of the filters odd. So always go for a size filter, this size filter, for example, 5, 16, something like that, 5, 7, 3, 9, and stuff like that. This is the size of the filter. This is the input channels. So it's always, the first one is going to be 3. Unless you're working on grayscale images, it's going to be 1. Or for example, you're working on some higher dimension images, such as MRI scans, it's going to be like, depends on the number of layers in the scan. And this is the number of filters. So the number of filters, just throw in a random number and go from something that increases. So here we started with 6, going to 16. Next should be, I don't know, 32, just something that continues to increase. And yeah, so these two numbers are easy. The first number, the last number is the one where you're going to be just make a layer, see what happens, make a layer, okay?
And also we don't need to define here this input shape. Like in TensorFlow, we need to define input
yes,
shape. Like
and no.
Okay.
So yes, you don't need to define it. If you're going to use only convolutional neural network, you can get away with having any size of image, but in most cases, you are going to just do the calculations on your own. So define your input shape and just go on and use it for all the images, right?
Here it could cause problem when you are flattening it, because you are flattening it with numbers.
Exactly. So in here, if you're going to use only convolutional layers, then it's not going to be a problem of the size of the input. So that's why PyTorch doesn't put this constraint. So just to allow you to use stuff such as the pure convolutional neural networks and stuff like that, to be more flexible, for the layers to be more flexible. It doesn't require the input shape. But if you're going to use stuff such as fully connected neural networks and flattening, then you're definitely going to need to set up your own input shape and respect it.
Where we define behavior of stride, I mean, if we have
stride, okay, simple, yeah. Usually in here, so let's check it out. There are area. How can I check? Yeah, I think like this, right?
Just wait a bit.
Here it is. Yes. Sadly, since you're okay, like this, there you go. Kernel size, stride, padding, dilation, groups, bias, by default is true. Padding mode, 0. You can check, let's go to view source. You can check here more information, I think, about each one of these variables, or each one of these hyperparameters, and understand when to use them, how to use them, what's the format, and all of this, right?
So in the create network, we will apply convolution, then remove and pooling. Do it 2 times. What view means?
View is reshape or resize.
So when we reshape, do to remove and
yes. So this is flattening.
Okay.
Right. Now we will get to the third important part of your model training, which is the training process. The training process is a bit simple in PyTorch. It's harder than TensorFlow, but it's because it gives you a lot of flexibility. So here you will find a lot of code for training. If you go to TensorFlow, let's go quickly to TensorFlow. Here it is, model.fit, very simple. Doesn't require you to do a lot of coding, but it doesn't give you flexibility. So why I like to use PyTorch, it's because it's very flexible. So first we create our optimizer. In this case, we will be using the stochastic gradient descent optimizer. And in cases where you might have different optimizers for different components of your neural network, let's admit them, for different components of your neural network, usually just send which component to its corresponding optimizer. This is very important for stuff such as GANs, for stuff when you will be doing domain adaptation later on, or stuff like that. You're definitely going to have lots of optimizers, different components, and each one is responsible for his own weights. Here we have the learning rate and the, okay, let me check.
SGD is what?
I didn't get, I think somebody raised them.
SGD.
Yes.
Stochastic gradient descent.
Stochastic gradient descent.
Okay.
It's the simple gradient descent. You can use Adam, for example. It's much better, but it's harder. It's better. You can use any other stochastic, any other optimizer that you want. Yeah, go ahead, guys. Ask.
Imad, we will cover like learning rate warm up on linear like warm up of learning rate and some other stuff like about training and different stages of training.
Different strategies of training. We will do this right. So let me just try to finish the lab quickly, and then we will speak about what are the different optimizers, different training procedures, and definitely there will be a part in the
about
homework. Yes, yeah, there will be a part in the homework where you will be asked to give me anything that you guys know, anything that you guys can implement. Extra will be considered as bonus points, right? So let's continue through it. So basically, we go for a for loop for all the epochs. So for example, here we have 5 epochs. An epoch means we're going to visit the whole data set once. So basically, we go through all the batches once, right? The second loop is the loop where we will be doing our, what is it called? Help me. Sorry. Is the loop where we'll be going through the batches, or this is an iteration, right? So this is an epoch. This is an iteration. In this case, we get the data from the train loader. We send the data and the labels to the, what is it called? To the GPU. We will ignore this and come back to it a bit soon. Send the data through the neural network, get our outputs. This is when the dot forward function is executed. So you don't have to do dot forward like this. Only thing you need to do is just send it. So basically net and send the inputs, and it will send it through the forward function that we just defined. It gives you the output, and you create the loss function between the labels and the output. In our case, we're using cross entropy loss because we have multiple layers and we are using classification. If you would like to understand when to use which loss, there is this good article that I wrote for some freelance guy. And basically here we just go through all the different scenarios, basically if it's binary classification, mutually exclusive multi-class classification, or non-exclusive multi-class classification. And each one of these, you will have its own loss function and how to choose them. It's a good article. You guys can take a look at it, right?
May I send a link in the group?
Of course, yes, I will send the link in the Telegram group, right?
Okay.
And then what we do is we back propagate the loss through the neural network and make one step with the optimizer. So this means that we're going and the updating the weights of the neural network. Why did we add this optimizer.zeroGrad? It's because this loss.backward, it calculates the gradients, right? And does not delete them. So in here, you made one step, that's true, but the backpropagated error and the backpropagated gradients have not been deleted. They're still inside, they're still existing. And if you have another optimizer that will make another step, they will be used. So this is why I like to make optimizer.zeroGrad to make sure that there are no gradients pre-computed that are still influencing the training process. So here you can add this here and add it right after, especially if you are going to be working with different components and different optimizers. Most of the problems will be in the gradients touching other components that they shouldn't be touching, okay? So just always make sure that the optimizer has no gradients computed. This is just for printing statistics, printing the loss. And here is just for visualization purposes. It's a simple code. You can easily understand it. So this is not really something that's related to PyTorch. It's mainly Python code for visualization and class accuracy predictions, right? So here we did the training for just a small one epoch. And there you go. So this was predicted to be a cat. This was predicted a ship. This was predicted a ship. No, this is predicted a verb, a bird, and this was predicted a ship. This was predicted a car, and this was predicted a ship. So as you can see, our model is quite catastrophic. So we have accuracy of 48%. So this is horrible. What you can do is simply train for 5 epochs, and the performance will increase drastically. Now we will be doing something else. So basically, this is the same thing again, but we will be doing transfer learning. So in this case, our model is much simpler. As you can see, there are not lots of layers in here. There's not a lot of work, as you can see. So it's very simple. What we will be doing is we will create this. The network is the pre-trained, what's it called? ResNet 18. We will freeze all the layers. How do you freeze a layer? So it's basically a self.net.trainable to false. If you want not to freeze the whole network, but a specific layer. So for example, let's go up here and see what are the different layers. So for example, I want to freeze layer 3. I can easily access layer 3 directly with code from here, right? Self.network.layer 3. Here you have it. If you want to access the convolutional part of this layer, you do .conv and you have access to that layer, to its weights, to its parameters, all of it. So this is why this PyTorch is very flexible. It allows you more freedom to access the layers, access the weights, access the activation functions wherever you are, right? Once we froze all the weights of the neural network, only thing we did, we changed the final layer of classification of ResNet and created it using our own linear or dense layer, which has 10 classes as output because we're using CIFAR 10, right? So this is the number of classes, and this is the dimensions of the pre to final layer activations, right? And then we just send it through the network, and that's it. The rest is very easy. So you can see, even though we trained only for, sorry, what just happened? Okay. Even though we trained only on one epoch, there was a huge increase in accuracy. So from 48 to 83, this is just for one epoch. I would recommend going to, for example, 5 or 6 epochs easily, and you will have even better results. Let's go quickly to the TensorFlow way. I will not explain a lot. I will just say that this is bad and show you guys how it's done very badly. So basically, you will be using Keras layers. It's an easier way to do it, but it's still very ugly. Here, you will get the data. Pre-processing the images, as you can see, is done manually. So you're using NumPy arrays, and you can just go ahead and pre-process them easily. How do you create a model in Keras or in TensorFlow? You're using the sequential API. So basically, you create a sequential model. Sequential model means anything that is like fully connected neural network or something that just goes step by step. So there are no big problems in it. And you start by adding your layers as follows, right? So basically the number of filters, the size of the kernels, the activations, and the input shape. Here, again, same thing, max pooling, dropout. Let's continue, and then we just go back to dropout quickly, flattening, and then a couple of dense, a dropout, and a final activation layer with softmax, right? You compile your model using an optimizer. So you see, it's very simple. It's a very small amount of code, but I think it doesn't allow you a lot of flexibility. So here we just specify the Adam optimizer for the whole model, sparse categorical cross entropy for the training. The difference between sparse categorical cross entropy and categorical cross entropy is also mentioned inside this article. You could read it, it's pretty simple. And here you can specify the different metrics, for example, accuracy, F1 score, and patati patata.
Matt, maybe I can go to one step back, just for a little bit.
Yes.
May I repeat quickly what we have done here, like the difference between PIS and PyTorch? I haven't
Yes.
get.
Remember, in PyTorch, we created a new class, defined the layers separately, and then we defined the forward or defined the flow of the input through the layers in a separate area. So here we define the layers, here we define the flow of the input through the layers. In TensorFlow, you don't have this. You define the layers and you define the flow. So it's a static graph. It's like this. It will always be like this. You see?
Like I think Keras now supports functional API, which
Yes,
gives you more
we will speak about
flexibility, but
this.
not as PyTorch.
Yes, we will speak about this right after this one. So we will speak about this right after this one. For the sequential API, as you can see, this is what a static graph is. You don't have the flexibility to put an if statement here. So for example, I put if x bigger than 5 model.add something else. So this will not work, but in PyTorch, this will work easily and you can use it however you want, right?
Yes, thank you.
But when it's useful, I mean,
when is this useful? Usually it's very useful for stuff such as Siamese networks, such as anything that is related to research, where you're gonna have access to the different values of the outputs of the layers. You're gonna make different decisions based on the images. For example, you get an image. If this image is similar to image X, we will feed forward it through this layer, or we will send it through this layer. If it's similar to object Z, we will feed forward it through another layer. So this amount of control is very useful.
So it's like
in research.
Three of decisions, right?
You can do anything you want. You can do a tree, you can do a for loop, you can do anything you want. You are free to use anything that is inside Python.
Actually, like the paper recently published by Facebook Lab,
yes.
Actually is X3D. Actually, we abuse this like a flexibility of PyTorch for creating the model like by itself.
Exactly.
You may read it out.
That's amazing. Yeah, that's a good example. So basically, you're creating more layers, or you're adding more layers while you are training, for example. So you can start training just one layer, and then you start adding more layers as the training progresses. So this is something that you can easily do with PyTorch using an if statement and a for loop. But for TensorFlow, it will be very difficult to use it in the sequential API. So as you can see, the sequential API for the training is very simple, just model.fit, model.compile. Very simple, very few lines of code compared to what we had in PyTorch, right? But PyTorch allows you more flexibility. Here also, if you'd like to evaluate, it's model.evaluate. For PyTorch, you're going to have to write the whole reasoning of the evaluation. We will just quickly show how it's done in PyTorch 2.0 and just maybe explain some of the concepts here. So here, data reading, same as usual. Yep, same as usual. This is the data loader. There you go. So from tensor slices, you shuffle, you make batches. So here it's starting to look again like, what is it called? Help me out, like PyTorch, right? But it's a little bit different. I think PyTorch's functional methodology is much better than this one, but still. Now, how do we create the model? Again, starting to look very similar to PyTorch now. So basically you have your layers in here and you define your forward function, which is what they call function in here. And here you just specify how the X will be flowing through your neural network. In here, you have a lot of freedom also to use if statements. You have for loops, anything you want to add, you can do it. But I still prefer PyTorch. Yes.
What's the difference between TensorFlow and Keras?
Yes. So basically, Keras, TensorFlow started out as a very promising framework provided by Google, but it was super difficult. Unless you are like a Google engineer with a PhD, you will not be able to just even start with it. So there was some French guy, he just created Keras. It was just like a small wrapper around TensorFlow and other libraries to allow you to get a beginner start, right? To just build a classifier, you only need a few lines of code. So he started as a sample library, which is completely independent from TensorFlow. Then TensorFlow started getting a lot of hate for its difficulty, and they decided to just buy Keras and merge TensorFlow with Keras. And now Keras is being developed by TensorFlow inside, being developed by Google inside the TensorFlow team. So just Keras is a different method of creating models, or a simpler method of creating models using TensorFlow, right?
When we want to use TensorFlow instead of PyTorch?
When do you want to use TensorFlow instead of PyTorch? If PyTorch is not installable on your machine, or if PyTorch is not fast enough for you. So if, for example, you have a constraint from your client that they need to use stuff from TensorFlow extended, for example, they already have a existing infrastructure that is relying on TensorFlow, then in these cases, and these cases are actually a lot, you're going to have to use TensorFlow models. Especially in the industry, you're going to have different clients who already have a system running. You can't just come in and destroy everything and start from scratch. You're going to have to work with what they have, and usually TensorFlow is what they have. After we have the optimizer, we have the loss. We have the loss. We start by making the training loss, training accuracy, testing loss, testing accuracy, and then the train step, test step. We wrap them inside this TF function annotation because it makes things faster, makes calculations much faster. And basically using this gradient tape, you can consider the gradient tape as what we said, as we've seen before, the thing with one step and not taking the step. So this helps you to define when to take step and when not, and to keep lots of gradients of different epochs still together, if that's something you would like to do. Simply, we send the images through the model, and then we calculate the loss, calculate the gradients, and then apply the optimizer. We calculate the training loss and the testing accuracy. Here we have the testing function, which is quite similar. We just take it through, take the model through it. In here, we don't have any gradient tape. We don't have any, of course, calculating gradients or making a step in the direction of the gradients. Only thing we do is calculate the test loss and test accuracy. And this is just a simple for loop where we go through the epochs and we make the training. Inside this epoch, each epoch, we iterate through the batches and the, what are they called? The iterations, basically, yes. And here we can see how it's starting to look like a PyTorch feeling, but it still lacks a lot of stuff. I don't know, Google is very complicated and always very difficult to use. So this was it. Do we still have just enough time?
For what?
To explain dropout. I really want to explain dropout, and then I want you guys to ask questions.
Yes.
Okay, yes.
What is the time limit?
We have time till 15, as I remember, so we have enough time.
Yeah, we still have time. Even for this, for the lab, we still have time. So what is dropout? I remember, I think, if I'm not correct, if I'm not mistaken, it was Mohammed Ais who explained dropout earlier. So basically, dropout allows you to close or ignore the output of a certain neuron or of a random neuron. This will help your neural network not overfit or not rely heavily on this neuron or on the working of this filter or this filter. So your neural network will be able to generalize a bit better. It will also be considered as hyperparameter tuning, but this is just something to think about, okay? So imagine that you are, every time you just drop out some of the neurons, it's as if you are looking for new architecture of the neural network, right? It's like you are searching the space of different architectures or the space of viable architectures and finding the best one, right? So basically, it's as if you are changing the architecture of your neural network and trying to train different neural networks at each time. And this will help you reduce kind of the overfitting of your model. Can somebody tell me anything, ask any questions, just anything you guys would like to say? We're here for it. After that, we will take a small break of I don't know how much time, and we will go through the second lecture of explainable AI, interpretable and explainable AI.
So in first version of TensorFlow, it will be like TensorFlow, and now it looks like more PyTorch, yeah?
Yes, so basically they started with TensorFlow, ugly, horrible, difficult to use, and then they just switched to the same format as PyTorch with more flexibility and more ease of use. This was mainly due because at a certain point, TensorFlow was starting to lose all interest from the research area, and PyTorch was also going up with the industrial applications area. So TensorFlow was quite slowly going away from the market. So they knew that they had to kind of adopt the dynamic.
Now it's the same speed of calculation. Now anyway, PyTorch is faster.
Yeah, exactly. Now even PyTorch is faster. Yep. Yes, Mohammed Awis, yeah.
So my last time I mixed up dropout and batch normalization.
Exactly.
But,
yes.
but still, I am still having hard time in understanding when do we use batch normalization and why do we need it? Like, we can simply use dropout.
Yes and no. So dropout, it drops some of the neurons in your layer. So for example, neuron 2, we will not look at what he says. Okay, so let's try to ignore what he says and try to learn even, so try to get his friends, for example, the other neurons, to do his job for him right now. So this helps your neural network extract more features, better features and stuff like that, right? And be more generalizable.
For a whole batch, yeah?
Yes.
Okay.
And batch normalization, you input a batch, send it through a layer. The values of the activation that you get after the layer can be very small or can be very large, right? So it depends. So it depends on the weights of your neural network. To fix this problem, usually what you should do, normalize first your input. Your input should be normalized. And after every layer, you normalize what you get. You normalize the output of every layer in order to make sure that the values are not too small, are not too big. They're always just right, just good. They're very good for calculating the gradients. The gradient will not be too big that it will cause you to get some NaN errors, and the gradient will not be too small that will not make enough steps. So this is very useful for these kinds of cases.
This is now understandable and very clear. So
Thanks.
we do drop out when we are training, and we don't do it while testing.
Inference.
Yeah?
Exactly. Yes, we don't do it on inference. The good thing, you can use both of them after every layer. And if you don't know what to do, usually just come here. Come to ResNet, look at the architecture of ResNet and see. For these guys, they didn't use any dropout.
Yeah.
So let's not use dropout. They use batch norm after every convolutional neural network, after every single convolutional layer, they use dropout. I will use dropout after every convolutional layer. So basically just try to check how these pre-trained big architectures use these functionalities and try to mimic them, right?
Okay. So this question might look very awkward, but I just
go
wanted
ahead,
to ask. This is very basic. So I know we make a model and we train on it. So what will happen when we'll test on it? Do we perform the same operation on testing data? Like we said, we will not use dropout layer, but it is part of the model.
Amazing. This is a very amazing question. And I personally should have spoke about this, but thank you for saying it. I think I should have this term here, eval. No, I don't have it. Well, that's wrong. So usually, before you go for the testing, you must write this. So it's called network.eval. And basically, it tells your neural network that you are in the inference stage. And in this case, many of the tricks or the things that you used only for training will not be used, okay? So for example, dropout will not be included after you apply this, call. So basically you apply network.eval, and this is how you tell the neural network, do not use dropout.
It's
apply
only for dropout.
Yes, I think as far as I know, the only thing that is in training and not in inference is dropout. There could be other stuff, but I really am not sure about this. I'm sure that back propagation, batch normalization still is existent in inference, but stuff such as dropout, it doesn't exist in inference, and you can filter it out using the network.eval function call.
And TensorFlow, it does it on itself, yeah?
Yes, it does it on itself. So basically, if you go inside the eval function and look for it, it's
in TensorFlow, it is done on its own. We don't need to like specify it.
In TensorFlow, I'm not sure, but let me see. Yes, here it is. It's defined like this. So basically, when you say training equals true, it will be using dropout. When you say training equals false, it will not be using dropout.
Thank you. It's like
You're welcome.
Now.
Nice. Do you guys have any other questions?
Actually, like during the interviews, actually, to the companies for data science positions, actually, we are asking about the dropout and what the model will do during this inference stage. And actually, it's like some kind of specific about dropout, like how to process it without, like it's not in some cases just it's okay just say training equal to false or net.eval, but in some cases like you need to explain how model will adapt in this scenario. It's not so easy.
Where we define it?
I didn't understand it. Did you say something?
Where we define it?
Here
we're going to use
dropout.
Yes.
There you go. So basically, we made a convolutional layer, another convolutional layer, another max pooling layer, and then we added dropout.
So it's going to work for layers after or before?
It's going to work for the previous layer. So basically, it will look at the output of max pooling and ignore some of its activations. So for example, let's say activation layer of dropout is a matrix 2, 4, and 5, 6, right? Randomly, it will ignore the last 6 and the 4. It will only leave 2 values in there, and the rest will give them 0.
And in some way in PyTorch, or you're writing it at the same time as you're defining layer?
What do you mean?
Yeah, I mean in PyTorch.
Yeah, in PyTorch it's also very similar. So basically, it's the same thing as using pooling and stuff. Let's check it out here. Dropout. PyTorch, right? Let's go. There you go.
Okay, I see.
Yeah, so it's another layer, and you can easily use it directly. Oh, we are at 1.8. That's nice. Okay. Again, there are different layers: dropout 2D, dropout 3D. Unlike in TensorFlow, TensorFlow takes dropout as a general thingy, so it works for both max pooling and for fully connected layers. But in here, just pay attention, just make sure that you're only using the appropriate type of dropout for every layer, right? It's awesome. And it's parameterized with the probability of dropping. So 0.5 means you will drop out half of the weights. And it uses a Bernoulli distribution to decide. Do you guys have any other questions, or should we take a small break?
About a function in PyTorch. train evaluation a bit lower.
Yes.
And line 44.
Yes.
What we are 45, 45, and 40.
Yes. This just means do not calculate the gradients. So if you do the training, it will calculate the gradients. Here, this just makes sure that there is no gradient calculation being happening.
Does eval mode automatically turns off gradient calculation?
That's a good question. Eval mode grad computations, right? Okay, let me just take this a bit here.
Actually, Maxim wrote in chat about comments from a Python developers about what ModeEval is doing. Actually, according to this, I may say what AN dropouts and batch nomination work differently in France. And actually, it's a good practice to use both eval and torch no grad.
Exactly. Yeah. So preferably just use both of them. If torch no grad doesn't do it on its own, then eval will do it. If eval doesn't do it alone, then torch no grad will do it. Yes. Yeah. Go ahead. Mohammed, Awais, yeah.
Sorry, I forgot to turn it off. It was like a few minutes ago. Sorry.
That's cool. That's cool. So
I sent you a message in chat on your Telegram. Please read it.
Yes. I will check it right after the finish lecture.
Thank you.
If you guys have no more questions, I will share with you on the chat just a small information. So yesterday we were having just a small discussion after the lecture, and we decided that after every Friday we will just have a small conversation. Just all of us. It's not a lecture. It's not guided. Just maybe some of the people who are working in the industry right now will come give you some of the tips, tell you some scenarios that they're working on. Just podcast. You can think of it as just a podcast, and you're like communicating, speaking, getting some experience from me and from the other people who have worked in the industry. I think we have some who have worked for 3 years in the industry. So that's going to be very useful for you guys to see how are things really done in there.
Good idea.
Хорошо.
Iman, maybe we have a break for example, for lunch.
Yes, of course. This is very, very much needed. Also, I need a break for breakfast in here. So I think it will be nice. How much time do you guys need? I know you guys have to go to canteen and stuff, so it might take a lot of time. How much time do you guys need? Let's make
30 to 40 minutes.
40 to 50 minutes.
Let's go for 35. Huh? Let's go 35.
35. Okay. 35. Okay.
Okay. Nice. 35. The good thing about the final lab, it's going to be a very easy lab of interpretation. So it's not gonna have any explanations done or anything. So basically, all the explanation will be in the lecture. The lab is just one line of code that you should just write, and it will do the whole code for you, right? So the lab is going to be very easy. Even if you don't make it to the lab, all you need to do is just read it, and you will understand everything. Just make sure that you attend the lecture, and hopefully by next week, we will find a solution for this problem of 3 consecutive lectures, okay?
Okay.
Today we have a lecture, right? After in 35 minutes.
Yes, in 35 minutes. Yes, Maxim, it's 11:35. Huh?
How long does it take? Lecture.
Basically, we will try to do the lecture and the lab however long they will take. We will try to finish them quickly so that I know that there are some students who have meetings at 2. We must finish the lecture before 2, and we must finish the lab before 3.
Oh, thank you.
Yes, yeah, that's true. Yeah, that's true. Yeah, okay. So at 12:35.
See you.
You guys at 12:35. Bye-bye. Let me make sure that they finished the recording. Хорошо.